So the normal distribution is such a vast theme or aspect of inferential statistics that we could describe it as the central theme of statistical analysis. So again, we're going to be looking at it in depth. We're going to look at the following objectives for this very class. I expect that at the end of the class, you will be able to compute for probabilities from the normal distribution and how to use the normal distribution to solve real-time problem. And then we look at how the normal probability plot can help us to determine a set of data if a data is approximately or normally distributed. So again, the continuous probability distribution is the distribution of continuous variables. And a continuous variable is a variable that can assume any value on a continuum. An example is the thickness of an item. These are values that can assume value between two whole numbers. We call them continuous variable, like numbers that may occur in decimal fraction. Okay, like you talk of the time required to complete a task, the temperature of a solution, height in inches. Now, again, these are values or variables that can take any value depending on the precision of the equipment we're using for our measurement. Now, the normal distribution has been described as a bell shape. It is symmetrical around its mean. It has its mean equal to the median and the mode and the mode. The normal distribution function is like a model with which we can study biological data or data sets. Again, when we pick data from a population, say a unique population like a cohort, and we plot the data on a graph, we will always end up with this curve shape of our normal distribution, rising to the peak and then falling. So the spread of this particular curve is determined by the standard deviation, while the position of the curve is determined by the mean. Either call it the position or the location of the curve is determined by the mean. And our random variable has an infinite theoretical range. It means when you look at this particular curve, the curve does not actually touch the line, the horizontal line. So it tails to infinity to the left and also to the right. That is why we say the random variable has an infinite theoretical range from positive infinity to negative infinity. So the normal distribution density function, here we have the formula. Never mind, this formula is not going to be a problem because to much extent we're going to depend on the one in this particular bracket. Okay, that is the one we'll be using to calculate our z-score. But it's important we understand the mathematical expression itself. Okay, the E is a constant, while our theta is also a mathematical constant. And again, we have our mean, which is the population mean. And then we have the standard deviation of our population, and x is any value of the continuous variable. Okay. Now, by varying the parameter mean and our standard deviation, we can obtain different normal distribution. What we are saying is that when our mean changes, it affects the kind of distribution we're going to have, either the mean or even our standard deviation. Take a look at these different normal distribution curve, A, B, and C. A and B have the same mean, but different standard deviation. So when you look at A and the B, they have the same mean. You can see the peak of the two curves is located at the same point. So we say they have the same mean, but different standard deviation. You can see the slope points of the two curves differ slightly. So we say A and B have the same mean, but different standard deviation. While for the B and C, we say the B and C have different means and different standard deviation. This is our B and this is our C. For the mean of the B, it is located at this center, while the mean of the C curve is located at this point. So they have different mean, and of course when you look at the slant, okay, the slope is also different they are also different from one another. So we say the B and C have different mean and different standard deviation. Now let's say we have a data set 2, 4 and 6. Of course our mean for this data set is going to be what? The mean for the data set is going to be 4. So, but let's say we have another data set, okay, 3, 4, 5. You will also observe that the mean of both data sets will be what? Will be 4, okay? But one thing is important here. The standard deviation of the two data sets are different. For the first data set, the standard deviation is 2, while for the second data set, the standard deviation is 1. So you can appreciate it is possible for our distribution curve to have the same mean like in the case of A and B, but different what? Standard deviation. Okay? The standard deviation talks about how scattered the individual observation within our data set is. So for the first data set, it looks a little bit scattered apart compared with the second data set. So that is a good way to illustrate what we have put in this picture. Now, again, it is important to have a clear understanding of this normal distribution curve. I've mentioned again that when we alter the mean, it shifts our distribution either to the left or to the right. If our mean increases, then our data's distribution will be shifted to the right. This is the right side of the curve, and this is the left side of the curve. Another way we can describe it is to say the upper and the lower end of the curve, or we can say above the mean and below the mean. These are different ways we can describe the different areas under the curve. So again, changing the standard deviation will also increase or decrease our spread. Okay, the standard deviation, if we flatten this curve the more, is going to increase our standard deviation. Meanwhile, if we try to compress this curve at this point of inflection, then our standard deviation is going to decrease. So it's important to understand these dynamics as it affects our normal distribution curve. Now, any distribution can actually be transformed into standardized normal distribution. What we are saying is that when you obtain data sets from a population, or maybe the sample from a population, we can transform that data set into a standardized distribution. Okay? We have our frequency curve plotted using our normal data sets. Now, to study that data set, the best to do is to standardize that data set so that we have a standardized normal distribution. How do we do that? We will make use of the random variable x that we obtain from that data set. We convert it into what? Our z unit. Okay? We convert them into our z units. And with that, we're going to have our frequency distribution on one hand, and then our standardized normal distribution on the other hand. Now, the standardized normal distribution Z has a mean of 0 and a standard deviation of 1. That is important to take note of. So, but how do we standardize? We standardize by translating our X to what? To our Z. Our Z is described as a Z-score, or better still, we call it the standard normal deviate, or the critical point, or the percentage point. Now, how do we obtain our Z? We obtain our Z by subtracting our mean from our random variable, and then we divide it by our standard deviation. With that, we obtain the Z value for every given X value. And having done that for our data set, we have standardized it. Now, let's look at this practical illustration. Let's say we have a class of 4 students, and these are the body weights obtained from individual students. Now, we can calculate the mean, of course, of this data set by summing them together and dividing by 4. And then we can calculate the standard deviation of these data sets as well. It will be important you attempt this so that you can get familiar with how to calculate the mean and also the standard deviation. But that is not our main focus. The main focus is that we want to generate the standard normal deviate for each of these random variables. So using the formula I've reviewed in our previous slide, we can calculate the z-score for each of our random variable here by subtracting the mean that we have obtained from individual random variable, and then we divide with the standard deviation we have obtained. It will be nice that you pause this video, take a moment out and do this calculation so that you can be familiar with how to calculate our z-score. Now again, we come back to the formula for our probability density curve, which we have explained before now. And again, I've mentioned the fact that by the time we are able to generate our z-score and we use it to construct our curve, don't forget that the mean will be 0 and the standard deviation will become 1. So the value above our mean to the right are described as positive z value, while the value below the mean are described as negative z value. Let's have an example here for clarity. Now let's say x is distributed normally. X is a random variable and we're given a mean of $100 and a standard deviation of $50. The z value, how do we calculate the z value? Our z value will be calculated by subtracting our mean, which is 100, from our x value, which is $200. And when we do that and divide by our standard deviation as stated here, we're going to get 2.0. So it simply means that a z value of 2.0 is what corresponds to a random variable x, which is equal to $200. Now in practical terms, what does this mean? This means that our x being equal to 200 is 2 standard deviations above our mean of 100. Recall, when you sketch this particular curve, our mean, which is 100, will be at the center, while this random variable s will be to the right hand side or above our mean. So, but with the standard deviation of 50, it simply means that from our mean, our random variable s is 2 standard deviations above this particular mean. I hope that makes sense. Now, another example we're going to look at is the score on VPH 527 test, where we got an average of 80 with a standard deviation of 6. Now the question here is, what is the z-score for a student who earned a 78 on the test? Now the usual way to calculate again is to subtract our mean from our random variable x. Our mean is stated as 80. Random variable x is the 78. Now when we subtract that and divide by our standard deviation, what are we going to get? That is minus 0.33. Please, it's important to take note of the negative, the fact that this is a negative value. So it simply means that this point will be below our mean to the left hand side, not above the mean. Anything above the mean should be a positive value, while numbers below the mean are negative value. Now, what does this mean? Again, in practical terms, it simply means that the student who earned 78 on the test is 0.33 below the mean. Now, ordinarily, if a student had earned 78 in a test, if we don't have detailed information about the test and the general performance of other students, we are likely going to think that probably this student or this candidate actually had the highest score or has actually done or performed very well. But looking at it relative to the general performance of the class, we could see that this student actually performed below average. Now, this is now the beauty of standardizing a data set. When we standardize a data set, it gives us a better understanding of the standing of our random variable. So, but let's compare these two examples for clearer understanding. Let's say a set of 2018, another set of 2019. Now, in 2018 set, John scored 78. And for that his class, the standard deviation is 6, while the mean score was 80. For James' class, James scored 80, while the standard deviation for his own class is 5 and the mean is 85. Now the question now is, which of these students in the different years performed better? Which of these students in the different years actually performed better? Now let's go ahead and do our calculation. And what is the calculation? We're going to translate this into our standardized normal distribution by finding the value, the z-value of individual random variable x that we have in these two normal distributed data sets. Okay, and when we do that, we'll realize that Jones has a z-score of minus 0.1 and 0.33, while James had a z-score of minus 1. Now, from this, you will agree that James' score is, both James' score and Jones' score are both below the mean. That's why they have negative value. But James' score is further below the mean than Jones' score. So it means Jones actually performed better than James. But when you look at the absolute value, the actual value they score, okay, we can appreciate that James scored 80, Jones scored 78. But from the comparative analysis using our standardized normal distribution, it is observed that even Jones performed better than James. Now this is what we're trying to achieve with our normal distribution. So the 0.33 standard deviation is below the mean, and 1 standard deviation below the mean as well. But from the look of things, James is further below the mean than Jones. Hence, although James scored 78 among his sets, he performed better than James, who scored 80 among his sets. So this is what we call relativity, okay? And it is a fair way of comparing two data sets. Now, when we plot our information on the curve, you can appreciate that if the mean is here, and Jones has 0.33, standard deviation or the z-score from our mean, and James had this, it means Jones is closer to the mean and even higher than James. Good. Now, another important thing we'll discuss is how to compare our x and our z. We have been doing this, but for better understanding, this is how it is illustrated. So the example we just discussed, the $1, $100, and $200. If you sketch this particular curve and you label them accordingly, you have your $100 as the mean, and then you have $200 as the random variable x. And then after standardizing it, where we obtain our z-score for 200 to be 2, then our mean is going to be 0. And from this particular curve, you can appreciate how we do what we call translation. We have just transformed or translated our normal distributed data to a standardized normal distributed data. And it's important you understand how this is labeled for better understanding. Now, these are some of the dimensions we will be able to solve going forward as far as this topic is concerned. Just like we have just mentioned, we can use our normal distribution to compare scores, okay, to compare standard score of different data sets. And then we can find probability finding. We can also calculate percentage of our data sets. We can also conduct proportional assessment and even calculate specific number of observation. Now let's start by talking about how do you find normal probability. Probability is measured by the area under the curve. Again, we have discussed this in our first class. Please, if you have not gone through that first class, it's important you go through that first class. It will make this class a lot easier. So, looking at this particular curve, you can see the portion under the curve is completely defined. Recall that the entire portion under the curve sum up to be 1, or you call it 100%. Half of the curve will be 50%. The second half will be 50% if you are expressing in percentage. So when you have to find the probability of a portion under the curve, say A less than or equal to X, X less than or equal to B. It means we want to define a portion under the curve from A to B. This is what all this actually means, okay? And you can put it this way, and you can as well write it this way. Inequality sign greater than or equal to, less than or equal are seen as the same, okay? So your greater than or equal to and greater than are both the same. Less than or equal to and less than are also considered. So often we don't introduce or equal to here since they are actually the same. So we can find the probability of a portion under the curve But please take note, the probability of any individual value is described as 0 under normal distribution. And the total area under the curve again is 1. One half is 0.5. The second half is 0.5. Now, usually when we conduct inferential statistics, there's a procedure for stating our problem. You have to state the problem, okay? And the problem will usually be if x is randomly distributed and the mean of this is stated and the standard of that is stated, what will be the value? So that will be our statement. Now, the next thing is to standardize the value by translating our x value, our random variable x, to our z-score. And then we want to sketch this particular curve, and then we label it appropriately, and then we'll use our table. Now, it's important to understand that to calculate for probability, after we have obtained our z-score, we have to look out for that z-score in our probability table for us to be able to tell what the probability of a portion is under the curve. Now, we can use different tables. You may want to check online for appropriate table for normal distribution, okay? But if you are interested in learning this further, you can look at the description of this video. I'm going to provide a normal distribution table that you can actually use to solve this question. So, again, we have our example here. The probability of z less than 2.0 is giving us 0.9772. And this value is obtained from our table. If you have ever been familiar with the use of four-figure table and how to check number in four-figure table, this is not going to be in any wise difficult. So we see here that z less than 2, this is where our 2 is. And since z is less than it, it will be towards the left-hand side. And that is how we establish the area under the curve that is of interest. And looking out for the probability, it gives us 0.9773. Good. Now, this is a typical example of our normal distribution table where we can check for specific z value and use it to compute our result. Now, this is how the normal distribution table looks like. To the left-hand side, we have the z value, and it will be to one place of decimal. But to the horizontal row, we have still the z value, but this gives to the nearest 2 places of decimal. Okay, so it means if you are going to check up the z of 2.0, and recall that this, you are going to check this under negative standard normal distribution table, because this value, you are going to check this value under positive standard distribution table, because this value falls above our mean. It falls above our mean. So when you check under the standardized normal table, you look out for 2.0, which we have here, and then the last 0, the second place of decimal, is what you check on the horizontal row. For the vertical row, you check the first 2 digits. On the horizontal row, you check for the second place of decimal. So it is the value you pick at that point that gives you the probability of that portion under the curve. Now again, we are brought forward. These are practical exercise where you are expected to calculate the normal distribution and then compute for the mean and then come up with the standardized normal deviates. Okay, and from this we can also now calculate our probability point. Now, the general procedure for finding normal probability is clearly outlined here. The first is to draw the normal curve for the problem in terms of s. Then you want to translate s value to z value, and then you use standard normal distribution table. Again, we can also find the probability of any reference point and above. Now, for this, we have find the probability of x less than 18.6. We can find probability less than. We can also find probability of what? Of an area greater than from a reference point. In this example, let x represent the time to take in seconds to download an image file from the internet. Suppose s is normal with a mean of 18 seconds and a standard deviation of 5 seconds. Now the question now is, we are to actually calculate, we are to calculate our z. How do we calculate our z? As usual, we subtract our mean from our random variable x and divide by the standard deviation, and that will give us this value. So this is our frequency distribution we plotted on graph. Now to transform this frequency distribution to standardized normal distribution, we converted the x variable into what? Into z. And this is what we have obtained. So for our normal distribution frequency curve, 18 is our mean. And then standard deviation is also given. Okay? So, and when we calculated this, we arrive at what? We arrive at 0.12 as our z value. As our z value. Very, very important. So what we have done is that we have translated our frequency distribution to our standardized normal distribution. Again, this is how to check our table. This is how to check the curve and do our computation. Now this is area again below. And how do we check this from our table? Our 0.12. So you are going to check the first 0.1, okay, in the vertical axis of the z-score table. And then the remaining 2 places of decimal, you want to check the value under. So this is the point of intercept. And this value is our probability based on what we are to calculate. Now the next point is how to find normal upper tail probability. In the recent example, the previous examples, we have been finding the probability of a lower tail probability, the lower tail of our curve. But of course, we can find the probability of our upper tail. Just the same way we did for the lower tail. So, and then we now construct our z distribution curve. So that's exactly what is done here. For our lower tail, it's important to realize that we got 0.12. Now, if you are changing it, that is z greater than 0. This, it means whatever we got here, the probability we got and the lower tail, we can subtract it from the entire probability, which is 1. And that will give us our final answer, 0.4522. And that gives us an indication of the probability of the observation above a particular reference point. Now again, we talk of finding probability between two values. We can also find probability between two values. We have 18, we have 18.6. So same way, we're going to find the z value for each. But recall that if the mean is already 18, it means the z value will also be 18. Now we have a z value here of 0.12. We can now compute, okay, and put it in this perspective. Our 0 less than x, z less than this. So we have established a particular range. We can now go ahead to our table to look out for the specific value of that range. So we have the probability of the first point, and then we have the probability of the second point from the curve. And when you find a difference, we're going to get 0.0478 as our probability of whatever occupies this middle area. Good. Now, we have discussed the probability at the lower tail. Okay? We can also calculate the probability of a range within our lower tail. It is following the same procedure of calculating our z-score for the lower our reference point, and then we calculate our z-score for our mean. And we can now bring the information together here and then make our deduction, and then we get our final answer for the probability of observation under that portion of our curve. Good. Now, as we round up, we're going to look at a review of the topic on empirical rule. In my previous class, if you have not gone through the previous class, which is the normal distribution part 1, you may need to go through it so that you can have a background understanding of what empirical rule is all about. So in this section, we're going to look at a little review or a brief review on empirical rule. It has been stated that for our normal distribution curve, between two standard deviation, plus or minus, and our mean, we have our total observation of 95.44% of our random variables. What it means is that 95.44% of our random variable for any normally distributed data set falls between two standard deviation plus and minus our mean. In the same way, 99.73% of our observations falls within 3 standard deviation plus or minus our mean. So we look at further implication of this. Now, given a normal distribution probability, we can find the value of our x. So we're going to look at the steps to find the value of our x. The first step is to find the z-value of the unknown probability. While the second step will now be to convert our x units using the formula. Now, this formula is very, very central to our normal distribution. We can find our x. Recall that the formula to find our z is z equal to x minus our mean divided by standard deviation. It is that same formula that we express in terms of x, so that our x will now be equal to our mean plus our z multiplied by our standard deviation. So if you are given a normal distribution probability, you can find the x, the random variable x. Again, we have an example here. Let x represent the time it takes to download an image file from the internet. Suppose s is normal with mean of 18.0 and a standard deviation of 5.0. Find x such that 20% of the download time are less than x. Now, what does that actually mean? It simply means we have our z indicated here as 20%. And then our mean is at the center, which is 18. Okay? So, the first thing is to find the z-value for the unknown probability. And when you look at the standard normal distribution table, you realize that our 20%, after you have sketched this particular curve, will fall to the lower tail of our curve. 20% is going to fall to the lower tail of our curve. How did we arrive at 0.2? What you simply do is that on that particular curve, the 20% area will be measured from infinity negative, which is 0.2. 20%, you convert it to decimal fraction, you have 0.2. And if you have 0.2, you look at the normal distribution curve table. You look out for this particular value, 0.2, or the normal number, the value closest to it. And when you look at the z-score table, you're going to find this value as the number closest to it. It's either you get the exact number or the one closest to it. Now, when you have established that very number in our table, then you trace it up and you trace it to the side. So you pick the value to the side, you pick the value up, and that is what will form your final answer. And that's how we arrive at 0.84. We have 0.8 here, 0.04 here, so we have 0.84. And because it is at the lower end of our normal distribution table, we add our negative value. Of course, the negative value is also indicated here. So the 20% is a probability actually, and when you express it as decimal fraction, that is how we arrive at 0.2 here. And then we go to our table to look out for that particular value, and then we are able to establish the z-value from our normal distribution table. Now the next step now is to convert the x unit using the formula given. Our x unit now will be equals to our mean plus our z-value and our standard deviation. The mean has been given to us as 18.0 plus our z-value we obtain is minus 0.84, and then our standard deviation is given as 5.0. So when we solve this particular calculation, we arrive at 13.8, and that is our random variable x value. It simply means that 20% of our value from a distribution with a mean of 18.0 and standard deviation of 5 are less than 13.8. I hope this is clear. You may want to pause a little bit, go through the video again so that you can have a good grasp of what this is about. Now, we are going to attend to the following exercise on you may want to use it as practice exercises that will help you to further understand this entire concept of normal distribution. We have several of the exercises here that can actually help us to have a better understanding of the topic at hand. Now, we're going to conclude with the topic determining the standard normal deviate from a defined probability. Of course, it's similar to what we have done. This is just a different directional view of what we have simply discussed. Usually, when you say, suppose we want to know the true value of z that encompass our 95% distribution. 95% distribution is a common reference point in statistics generally. So, but we can determine the z value that actually encompass that 95% distribution. So, of course, when you have your 95% at the middle, you are going to have 5% left out of 100. So, to the lower end, you are going to have 2.5, and to the upper end, you are going to have 2.5, since the curve will be divided equally. So you have something like this. For the 95%, you have 2.5 to this end, you have 2.5 to this other end. And from probability density calculation, you are going to arrive as a z-score of minus 1.96 and plus 1.96. Now, this can also be computed following the previous example that I have stated. Now, further exercise will also help us to understand the normal distribution very well. So you may need to take your time to go through these other exercises and the list of assignments here. So this will go a long way to establish your good understanding as regards the subject matter. So this is the much we are going to take for this particular class on normal distribution. Don't forget to like, share, and subscribe to this channel. And if you have any question as regards what I've discussed so far, don't also forget to drop it at the comment section. I'll see you again in my next class. Thanks for listening.